Hi, I'm Mary Bennett, and my poster is on my third-year university project, which has the title, Using Formal Methods to Review CGen's Formal Semantics. Can a RISC-V SAIL description be transformed into a CGen architecture description? As you heard before, SAIL is a formal descriptive language written in OCaml made by a group at the University of Cambridge labs. I used OCaml to get SAIL to transform or to write a processor-specific file that was taken by CGen. CGen then was able to generate a GNU assembler, disassembler, and there will be chance for a simulator. Thanks.
Okay, thank you. Mateos?
Hello, everyone. I'm Abdallah, and I'm presenting on behalf of Sapienza University of Rome. These are my colleagues. My supervisors are on the left side. Okay, and my direct supervisor is Mauro Olivieri. I switch like this. Okay. 1, 2, 3. Let's make it direct. Okay. So we have this family of processing codes called Classidra. And what I'm presenting today is a very, let's say, parameterized core. It's very configurable. We can configure the number of threads, the register file type. It's 4 pipeline stage. It has a mathematic accelerator, and it's connected to scratch pads. And let's say you can configure the number of scratch pads and the SIMD width for that accelerator. And we tailored this accelerator for like a neural networking applications. And we tried it on many different applications, starting from the lowest level, arithmetic operation, going to convolution 2D, and going to a set of convolution 2D results. And these are the results, and I will explain them more in detail if you come and see my poster. Thank you very much.
Okay, thank you. Now, Mateus. Sorry about that.
Okay, hi everyone. My name is Florian Glaser from the Pulp team here at ETH Zurich, and I'm going to present VivoSoc today, which is a RISC-V based mixed signal ASIC for miniaturized medical instrumentation. So we basically combine a 4+1 core RISC-V pulp processing subsystem with a multitude of versatile and flexible analog frontends designed for various types of medical instrumentation and signal types. So with VivoSoc, we are able to do acquisition and also simulation of biomedical signals, as well as processing and control within a single chip. And we have the fabricated chips, but also platforms based on it and complete systems. So one highlight is this so-called optogenetics head stage, which is smaller than 1 cubic centimeter and only weighs 1 gram, including the battery and wireless connectivity. And another example that I can demonstrate is a 4-channel EEG headband, which is also similar in size thanks to this level of integration. Okay, thanks.
Good afternoon. I'm presenting on behalf of my friend Manpreet. The important trend of microprocessor to improve performance is branch prediction and data value prediction. So the likelihood of previously seen value recurring storage is called value locality. If you see, there are 3 instructions. The third instruction for the value for defining value m, or to get the value of m, instead of waiting for instruction 1 and instruction 2 to complete, I can predict the value of m. So this is value prediction. Now I can exploit the value locality to do the value prediction The existing value prediction techniques are static, means that value prediction is done through compiler, but the research work focuses on doing value prediction through dynamic data flow analysis. So you can visit the poster, and I'll be there to explain. Thank you.
Hello, my name is Thiago. I'm from the CA in France, and I'm here to present the poster entitled Viral Precision Capabilities in RISC-V Processors. So the main motivation of the work is actually because a number of applications require a large or adaptive precision during the course of the computation. And the idea is then to explore viral precision with this by augmenting RISC-V with viral precision capabilities. In this sense, we have a RISC-V coprocessor that uses the UNUM formatting memory, an ISA extension, and a programming model for this. With the experimental results, we got 3 linear solvers, and we get a speed up of up to 18 times, over the baseline, which is the MPFR library. If you are interested, just come talk to me in the poster section. Thanks.
Hello, everybody. My name is Alexander Kamkin. I'm from Institute for System Programming of the Russian Academy of Sciences. At the previous RISC-V events, we presented microtask for RISC-V, a specification-based test program generator for microprocessors, shown on the right. So it consists of architecture-specific module describing instruction set constructed automatically from instruction set specifications, and architecture-agnostic generation code that implements various test generation techniques, including randomization and constraint solving. This particular presentation is about memory management specification. We have suggested an NML extension called MMUSL, Memory Management Unit Specification Language. It allows specifying virtual addresses, physical addresses, address spaces, buffers like page tables, translation look-aside buffers, and so on. So we have specified RISC-V address translation algorithm, and now are able to generate memory-related test programs automatically. So the tool is open source, is distributed under Apache license, so feel free to download it and use. So thank you.
My name is Antti Lukas. Sometimes I speak too much and too long. Not doing it today. I think it's time to make something and to make more RISC-V processors and system on chip. And the best way to do it is to make all FPGA in the world to make able to run C code in RISC-V, and that's doable. And I'm going to do it in 2020. So, thank you.
Yeah. Hi, I'm Onno. I'm with Trinamic, and we developed a RISC-V-based motor controller, or a motor controller with an integrated RISC-V processor. Here you see the RISC-V processor system, and this is a block diagram of the complete design. We have the processor and a very sophisticated servo controller integrated. And if you're interested in the product, you will be able to buy it next year via distribution. You will be able to program it and use open source tool chains to program it and to turn your own motor with it. So thanks, and please visit me and check out my poster.
So hello everybody, my name is Simon Kiki, and the work I present here is about embedded system where both performance and energy efficiency are important. So usually to solve this problem, we use heterogeneous multi-core system with both out-of-order and in-order cores. What I propose here is to add another type of processor in the system, which are VLIW processor. The problem is that those cores use an explicitly parallel ISA, and so you won't be able to easily migrate a task to the VLIW core. So to solve that, we add a layer of DBT, so dynamic binary translation, which is able to dynamically generate the explicitly parallel binaries. So we developed a platform called Hybrid DBT, which is capable of executing RISC-V binaries on a VLAW, and which also use dedicated hardware accelerators to speed up the translation. So come and see me.
Good afternoon, everybody. My name is Noordin Ait Said. I'm a first-year PhD student, and I'm working on this project as a parallel, in parallel with my PhD students. So the problematic that we are trying to resolve in this educational project is the fact that it's very difficult in the hard and not obvious to understand the link between the hardware and software, especially when it comes to beginner students. So we are trying here to use the rocket ship SOC generator from UC Berkeley, which is written in Chisel, which is synthesizable, and which is a highly parameterizable platform. So students can tune a lot of parameters, number of cores, sizes of the caches, etc. So we are trying to use this platform for education through a set of labs which permit students to go from all the way from the software until the hardware implementation. So if you're interested, please come and visit us in the poster session. Thank you very much.
So hi everyone, I'm Matheus, I'm a PhD student here at ETH, and today I'm presenting, I'm updating the state of ARA, which is the vector processor that we have been developing here in the context of the PULP project. So in my poster, I will talk about the microarchitecture and some implementation details of this unit that was based on RISC-V vector extension and has support for double, single, and half precision floating point. My poster also has a scalability analysis of this vector unit when you go up in terms of number of lanes, of number of functional units, and the performance limitations that come with. And I also present some results, some implementation results of the instance with 4 lanes, where we present our performance of up to 10 gigaflops, and an efficiency of 46 gigaflops per watt in nominal conditions. Thank you.
Hello, my name's Simon Davidman, and you would have heard me talk yesterday about our simulator that we've made freely available on GitHub, which implements the whole of the RISC-V spec, including the latest vectors and bit manipulation. But what I'm actually going to talk about here is co-verification, which is the use of getting software up and running, sophisticated software. And in this case, it was actually an SMP Linux running with a hardware accelerator, which actually was state-of-the-art vision analysis for automotive. Now, we've seen our simulator, but actually our simulator can be used not just as a CPU, actually a whole platform. It can model everything that you can put in hardware, and we provide it as a sort of standalone, or it can actually work in System C environments close to the EDA world. It's an example of a System C platform. And we have a relationship actually with all the major EDA system Verilog simulators and System C simulators. And this is an example that was presented at a Cadence conference earlier this year, where they've got an emulator and they take the RTL, they run it in the emulator, and actually in this application it was booting Linux on an SMP processor in the RTL, and it ran for over 24 hours, was the time it took to get to the interesting bits. And what they've done is built a technology which is what they call hybrid, where they hook up a software simulator such as ours to talk to the emulator, and that hooks through the left. And the performance they got out of it was pretty astonishing. It actually sped up the simulation 130x. So instead of taking a day or so, it was under an hour to get up and running. And in some of the cases, it got within a few minutes. So they could really get a lot of stuff done through the emulator. They're running an emulator which costs several $1 million, and suddenly we're making it 100 times faster, which is absolutely astonishing for them. And so this is verification of software running on top of the hardware with all of the RTL in there. So that's what the poster is about. Come and see us and we'll go through it in more detail. And of course, we can also talk about hardware verification when you've got an RTL core you're trying to verify. Thank you.
Hello, everyone. I'm Michael Gauci. I was a PhD student here at ETH, and I was working on the PULP platform. And then I switched to a company here, ACP, located in Zurich. And thanks to RISC-V and also the PULP platform, we are now able to not only build RF transceivers, but also full SoCs. So what we have here is our first SoC. It's a quad-core RISC-V processor, which can attach to the NB-IoT and ECGSM network. So what we use here is we have a Swisscom SIM card, and we can attach with this processor to the network and send data from sensors, and we can also control it over a mobile phone, for example. And yeah, if you want to see it, come check it out at the poster session.
Hi, this is Michael again. My company, Antmicro, is building the open source complex functional simulation framework called Renode. And in the poster, we're showing how Renode can be used to very flexibly co-simulate and co-develop hardware with software. So this system is our customer partner, Dover Microsystems, and they can simulate the entire system, including video peripherals, UARTs, lots of Dover-specific stuff, and work with it both in terms of design space exploration, testing, software development, as well as a customer evaluation and so on. All this because Renode is, of course, fully open source and supported by us. And my other slides are gone. So I won't be able to tell you anything else, apparently. Okay, so I would be willing to actually see my slides here, but I'll just continue to tell you what we're showing. What the poster contains is a whole hardware-software co-design flow, which involves modeling things in Renode for fast work, and then also simulating those things on an FPGA, where the work with Renode is multiple times faster. So it allowed Dover to go from several weeks to develop a new feature to several hours or perhaps a day to build something new. We allow to do this through a flexible language and scripting framework, but also we have additional functionalities such as co-simulation with Verilator, as well as we can actually co-simulate things between your PC and an FPGA. And by the poster, we'll be giving out FOMU, which is an FPGA and a USB port. If you can tell us that you're going to do something interesting with FOMU, and especially with Renode, you can get your own little FPGA board that will fit into your PC. So come and see our poster.
Hello, I'm Mukesh. I'm presenting on behalf of my colleague Nanda Palari. So Asling RISC-V is a IDE tool they are developing mainly for SWORD, and it's based on the Eclipse, and you can do the hardware and software debug as well as like multi-threading debugging also you can do, and you can do the heterogeneous processor debug also using that IDE. And we have a support of HTML-based register debugging as well as RAM and ROM-based debugging support also. And we can do the integrated RTOS debug using that IDE. And SWORD is nothing but a 9-stage dual issue pipelined out of order capable core with support like and 64. It has got like a core mark of around 4.05, I think. And thank you.
Yeah. Hello again. So when you try to multiply a number like 0.7 and 1.50, if you use a binary fractional calculator, that you get a number something like 0.73 after rounding it off to 2 decimal numbers. But as we humans use decimal fractions, if we do the same thing and if we round it off, then we get 0.74. And we expect all our calculations to be 0.74 or more of decimal. So in most of the scientific computation applications, since the rounding of error is there, so you can't use binary fractional calculations. So there is a need for decimal processing, which has to be in high precision, and a dedicated hardware is needed. So in my poster, I'll be telling about how I'm doing decimal processing and how I'm interfacing with RISC-V core. You can visit me at the poster session. Thank you.
Just a quickie. I told you everything about it already, so just to jump through the thing. Here's the varilator simulation, and that's the board we're giving away. I've said it all, so hopefully remember. Come talk to us, tell us what you're going to do with FOMU, and we'll give you one. You can work with Renode or without Renode, however you want. Thanks a bunch, guys. Sorry for the technical problems. They were unexpected, but hopefully you enjoyed the poster session anyway. Right now, we have time for a networking break. Please return here around 3:20, although we're delayed a bit, so I guess... No, we're actually on time. So yeah, 3:20 is when the sessions begin.
Thanks, everyone.